Now in this video, let's look at how to generate the necessary statistics using Excel's data analysis to do the two sample t-test or two sample confidence interval. Now this time, let's assume that the underlying population standard deviations are unequal. So I'll show you how to do either case, whether it is equal or unequal. So for here, let's take an example that's not in your textbook. Let's assume that we have sample starting salaries of randomly selected fresh graduates, people who graduated from our program in the last 1 year, and what were their starting salaries. So we have a random sample of HRM majors and then a random sample of marketing majors, and we want to test to see whether the average salaries are same for both the majors or are they different. So X sub 1 is starting annual salary for HRM graduates. So mu sub 1 would be the mean of that. X sub 2 is the same for marketing majors, and then mu sub 2 is the average. Now hypothesis is that we want to test whether the two means are same or not. It's a two-tailed test. Okay, now we want to use the data analysis command and not have to compute. We can use the same approach like before, but then we'll end up not being able to assume that the two population standard deviations are equal, in which case the computation of the degrees of freedom becomes complicated. So we will use data analysis. When you look at data analysis, at the bottom you will see a bunch of two sample tests. So we have a z-test when population standard deviations are known. Sigma sub 1 and sigma sub 2 are known. Okay, so we won't use that. So here we have t-test two sample assuming unequal variance, and then two sample assuming equal variance. Okay, they both give you about the same kind of format in terms of how the results are presented. Okay, but the computations are different, underlying computations are different. So we're going to use this one. So the way you would use data analysis if the population variances are equal is exactly the same. So you have to just highlight the data values and then click OK. Now if the samples are not independent, if they are paired sample, they are related, then that's the test that we have to use. So right now let's select that one. Okay, variable 1 range is HRM, so it's that. So notice that the sample sizes need not be the same. And then the second one. Okay, now the hypothesized mean difference is we want to test whether there is no difference at all. Okay, of course the first row is a label, so you have to check that. Okay, and let's put the output right there. Okay, and you click OK, then you get the results, and it gives you detailed results. So let's format it a little bit. Okay, the p-value, okay, I'm expressing that as a percentage. Okay, so notice what we have here. So we have the mean of the two samples, x bar sub 1, x bar sub 2. Variance, it is s squared sub 1, s squared sub 2. Observations is sample size, n sub 1, n sub 2. The hypothesized difference. And then the degrees of freedom. This is where the difference is. The degrees of freedom based on unequal variances, it's not the same as n sub 1 plus n sub 2 minus 2. And then we have the t statistic, alright, and then we have the one tail critical values and p-value and two tail critical value and p-value. So the output allows you to do either of those two tests. We can do a one tail test or a two tail test. So you have to make that choice, and since we want to do a two tail test, we'll ignore these two numbers, so not needed. Now we need only these two. Now, critical value approach. Okay, so t table here is the t critical. So that's your t table value. You don't have to compute the t table with t dot inv. Also, it's part of the output. Okay, so conclusion is the t value is 4.838. Since the t is greater than the t critical value, we reject the null hypothesis. Okay, and we can do a p-value approach. Here again, you don't have to compute the p-value using t dot dist. You can just get it from the output, which is a two-tailed test, which is that one. So conclusion is reject, obviously, and we provide an interpretation. So we have sufficient evidence to conclude that the average starting salary for these two measures are not the same. So now you can set up a box plot for these two if you like and present it. So here are the two box plots, and notice that the y-axis are exactly the same, and you can visually see the difference in the mean of the samples. And if you notice that the spread of the data values, a measure of say standard deviation, it looks like it's kind of same. So we could have assumed that the two population variances are equal here, but this is by way of illustration. If you want to do a test where we are not able to make that assumption, how do you do that? So that's this. You look at this as a way of illustrating how to do that test.